Geography is the study of places and the relationships between people and their environments. The environment could be built or natural, but geography seeks to understand questions like where, why, and how in the context of place. For example, if we're looking at a hurricane, we would ask where is the hurricane projected to go, and when is the hurricane going to hit landfall, and how will the hurricane move through space? Other questions we might ask are how will the hurricane impact the communities, and what will our response be as a result of the damage? Depending on your field of study, you might have a different perspective or different questions you might ask as a geographer. So the first example is a health geographer. They might be interested in how emergency response teams actually responded to the hurricane. Transportation geographers might be interested to know how traffic responded to critical link failures, so a highway or a major road being flooded or damaged in some way. An economic geographer might be interested to know how the governments are releasing and distributing relief funds in the areas affected. And a political geographer might be interested to know how the different municipal governments responded to the situation. In some research papers, you might get research questions or hypotheses. And this really depends on how you want to interact with your data. So a research question is often used to explore the data to see what it has to offer. Whereas in other cases, you might use a hypothesis. So you have an idea in mind already, and you want to test the data to see if your hypothesis is true. In these cases, you'll have what's called a null hypothesis, which is essentially that the relationship that you're looking at does not exist. So for example, if you're looking at lung cancer rates near a pollution source, your null hypothesis would be that living near a pollution source does not increase your chance of lung cancer. So next I want to give some context to research and hypothesis testing by looking at an academic journal. So this is just a random article that I pulled up here. And the first thing you'll see is the introduction. And basically the introduction is used to justify your research. So why do people care about your research? The introduction also has the literature review, where you've gone and collected articles about the same topic and talked about what they've done and what they found from their results, and also how your research fits into that greater literature body. So scrolling down here, the next section is the methods section. In here you'll find the data and study area information, if that's applicable, and the data is what we'll focus on in our lecture today, but I did want to give context to where that data fits into the greater research. And in this section, you'll also find the methodology, which is essentially the tools and methods that you'll use to complete your analysis. Next up, we have the results section, where you will put all of your outputs from your analysis. So any sort of analysis that you're doing is put in this section, and it is void of any sort of commentary or opinions that you might have about your results. Next up, we have the discussion. So the discussion is really the bulk or the importance of the paper. So you're taking results and you're interpreting them, and you're telling the reader why your results matter and what your results mean in the greater context of your field. And then the conclusion is just a summary of your key findings of the entire research. And really, I just wanted to go through a typical paper to give you context to where our lectures fit in to the greater research that you might be doing in the future. Next, we'll talk about geographic data. So this is a spreadsheet showing dog breeds in the United States and information about these dog breeds. So the first thing is this entire table here. This is all considered the data set, so all of the information that is being shown. Next, we have the observations. So observations are all of these rows of data. So an observation contains the main subject matter that you're looking at, as well as all of the data points that relate to that one observation. So in this example here, the observation is the Yorkshire Terrier, and it is considered a toy category dog. It's 5th in the US, and its lifetime cost is about $20,701. So all of this information in this row is considered the observation. The next thing is the variables. So each of these columns is considered a variable. So the first one being category, this is the category of the dog breed. And here we have popularity in the US, which is a rank order variable. And the next variable we have is lifetime cost in US dollars, and so on. So all of these columns are considered variables. And the next thing we have are data values. So data values are represented by a cell. So each of these cells are considered data values. And these are just the one instance of a number or in this case, a category that's associated with that dog breed. There are two types of data collection, one being primary and the second being secondary. Primary data collection means that you had some sort of involvement in the collection process. Either you collected the data yourself, or you were on a research team and they collected the data, but you had involvement in how the data was collected. So this is obviously better because you have full control over how the data is collected. And the other thing is that you understand exactly what the errors and the limitations of that data are. So you understand the quality of that data. The other thing is collecting data on your own is often very time and resource intensive because you have to go out and collect it. That takes time. It might take money because you're using materials or you're paying people to do tasks for you. So it can be very time and resource intensive in that way. On the other hand, secondary data means that you had no involvement in the collection process. So you have either downloaded the data from a website or asked someone to give you the data, and you had no involvement in how the data was collected or when the data was collected. One of the major pros of secondary data is that it is free, or in some cases you might pay a small fee to acquire the data set. And often the data is already considered clean, which just means that someone has gone through, corrected any errors in the data set, or just generally organized the data in some way. And because it's so cheap and easy to acquire, you can study a much larger population since you can pull data from different websites or different people to acquire a larger merged data set. Obviously, the major con of secondary data is because you had no involvement in the collection process, you have no control over how the data actually is. And you don't know the quality problems with the data. You don't know the limitations or the errors that might be in the data. In the context of variables, we should first consider population and area. Population could be people, as you would probably expect, or it could be something like trees, animals, or some inanimate object. The area refers to the place that you're collecting your data. So it could be something like a school, a city, or the entire country. When we're talking about population and area, there's some things we need to consider to avoid making wrong assumptions. So for population, there's something called the ecological fallacy, which means that when you're looking at population level or aggregate level data, and then you're taking the results of that and assuming something about an individual. So for example, in Canada, the most popular breed of dog is a Labrador Retriever. But it would be wrong of me to assume that your favorite dog breed is a Labrador Retriever. And to make that assumption would be an ecological fallacy. The modifiable areal unit problem is a result of looking at point data that has been aggregated into some areal unit. When we're looking at aggregated data, so point values that have been placed into some sort of container, we will often have issues based on the container that we use. So at a city level, we have things that are called census tracts, which are typically to house around 5,000 people. Now these census tracts vary in shape and size across a city, and because of that, when we're mapping out data, the data might show different things based on those areal units. So we have to be mindful about the assumptions we're making about our data based on how those areal units are constructed. There's another issue involving the segmentation of areal units, so the areas between two areal units. And if one case rate is really high in the left areal unit compared to the right areal unit, the line dividing those units doesn't mean there's going to be a stark contrast between 1 meter into the left unit and 1 meter into the right unit. So those are two things we need to consider when we're discussing population and area. In terms of variables, we can categorize them into two main types, including qualitative and quantitative. Qualitative data is any sort of categorical data, and categorical data specifically is data that's been grouped into at least two groups. So an example of categorical data would be something like your level of education. So you could have just high school, college, university, master's, etc. And binary, on the other hand, is a variable that is grouped into only two groups. So this would be something where the answer can only be yes or no. Quantitative data is any sort of data that is numeric. So discrete refers to data that is integer values, which means that there are no decimal places associated with the number. An example of this would be some sort of ranked scale, so the top 10 movies of all time, or it could be the number of people living in a household, since you can't have half or a fraction of a person. So continuous data is any numeric value where there would be a decimal place. So this could be something like rainfall or income. And it's important to note that these values could still be rounded to the nearest whole number, but they would still be considered continuous. So there are 4 different levels of measurement, which include nominal, ordinal, interval, and ratio. First, we have nominal, which is essentially just categorical data, but it's unique in that there's no implied rank order of the data. So an example of this would be land use in a city. A municipality will zone out parts of the city, and it essentially restricts buildings to that land use type. So for example, there are parks, residential areas, industrial zones, and retail zones, but none of these land uses are ranked any better or worse than any other piece of land. In terms of ordinal data, it's essentially the same as nominal in that it is also categorical data. However, the difference is that ordinal data can be rank ordered. And that implies that some categories are greater than or less than the other categories. So to continue on with the example from the last slide, let's look at land use again, but rank order them. So if you're buying a house in a city, you would probably have preferences about the land uses that were around your house. So you might rank the land uses according to your own preferences. So maybe you would want to be in a residential zone with parks nearby and probably some retail stores close by as well. And then probably at the bottom of your list would be an industrial zone. So in this way, you have taken categorical data and you've ranked it according to your own preferences. Interval and ratio are very similar, but the key difference is that with interval data, the 0 on the scale has meaning. So if we look at temperature as an example, Celsius and Fahrenheit are both considered interval data because 0 degrees Celsius or 0 degrees Fahrenheit are still measuring the amount of heat. Ratio is different in that the 0 means there's an absence of measurement. So to keep with the temperature example, Kelvin is considered ratio data because its 0 on its scale represents the absence of heat, or the point at which minimum kinetic energy among particles is observed. Next, we'll talk about measurement concepts which involve precision, accuracy, reliability, and validity. First, precision refers to the level of exactness of a measurement. So how close were your measurements relative to one another? This is often associated with the calibration of your measuring instrument. Accuracy refers to the system-wide bias within your measurements. It refers specifically to how close your measurements are to the true value. Precision and accuracy are often intertwined in the relationship to data. The most commonly used example of precision and accuracy is through a dartboard. Consider you're at a bar with your friends and you're playing cricket. You've already thrown several times and you've completed all of the numbers except for the bullseye. On your first throw, your 3 darts create this pattern, which is considered not accurate and not precise. After your friend throws, you throw again, and this pattern is considered accurate but not precise. Next, you throw another 3 darts, and this pattern is considered not accurate but precise. And on your 4th and final attempt, you throw this pattern, which is considered precise and accurate. Validity refers to measurement issues resulting from the definition or concept used. So often you could consider these to be proxy measurements, where you don't have a method to directly measure that thing you're looking at, but you can use other variables that are associated with that thing. So a good example of this is Maclean's magazine, where each year they rank the top universities in Canada. Since there's no way to directly measure how good a university is, we have to use these proxy measurements in order to get a sense of how good a school is. For Maclean's top comprehensive schools of 2021, they used student-faculty ratio, student awards, student satisfaction, faculty awards, library expenses, among others, to determine the ranks of the universities. Obviously, if you were ranking the universities, you might have another set of parameters or variables that you would value more than Maclean's. So you can see there's validity issues in the way that Maclean's has ranked their universities compared to the method that you might take. Reliability refers to the consistency and the stability of your measurements. And this is important if you want to replicate the methodology used by someone else in either time or space. So in the future, you want to replicate someone else's research, or if you want to go to a different location and you want to replicate that same study. An example of this would be if you went to a cocktail bar and you ordered a martini and you really liked it, so you asked the bartender for the recipe. And when you go home and you want to make it in the future, you realize, well, I don't have all of these ingredients. So instead of using Plymouth gin, you use Beefeater because that's what you have on hand. And you don't have Dolan dry vermouth, so you use your Martini Rosso dry vermouth. You don't have the house orange bitters, so you use Angostura orange bitters. You don't add the garnish, and you shake instead of stir. And you take your first sip and you realize, this doesn't actually taste anything like the martini that I got at the bar. And it's because you didn't use that same methodology and the same technique that the original bartender used. So effectively, you have a different drink. There are certain types of classification methods that help you organize, simplify, and generalize large amounts of data into meaningful categories. The most common methods include equal interval, quantile, and natural breaks. Equal interval is used to create groupings that are equal in size. Quantile uses the same number of observations or features in each grouping, and natural breaks looks for jumps in the data in order to create these categories. So I just wanted to give you guys an example of how we would actually classify data. And we can do this manually in Excel or some other program, but it's probably easiest to visualize in Excel. So the first thing we need to do is sort this data so it's in an ascending form. So first we're going to just highlight these two cells. They're the header cells. Go to the Data tab and click the Filter button. Now we can sort this column from smallest to largest. Now you can see they're in ascending order. So the first thing we need to do is find the range of this data. So we're going to go equals, take the largest number minus the smallest number, so B13 minus B2. Hit enter, and we see that the range of the data is 99. So if we want to divide this data into three groups, what we do is take the 99 and divide it by 3 for 3 groups. So we get 33. So each group will have 33, a range of 33. So for the first group, we can take 102 and add the 33 from down here. We get 135. So you can see here, this 135 value is actually in the data, so that is our first group. So let's go ahead and color these red. Now what we can do is do 135 plus 33, that equals 168. So you can see here there's no 168 in this data, and that's fine. That just means that these two values are within the next range of 33, and this 186 here is beyond this 168, so it's not in the group. So let's go ahead and mark these as green. Now for the last group, we'll do 168 plus 33, that's 201, so that means these last three numbers are in this third group. So let's go ahead and mark those as blue. So that's how you create equal interval groupings for a data set. So next up we have the quantile grouping, which means that there's going to be the same number of values in each group. So again, we need to first sort this data, so we have to create a filter and then click this down arrow and go sort smallest to largest. Now what we need to do is figure out how many data points we have in the table. So right here in Excel it says 13, 13th row, minus the 1 since this is the header row, which equals 12 obviously. So if we do 12 values divided by 3 groups, that equals 4 obviously. So we can just simply go 1, 2, 3, 4, and we will create that first group. 1, 2, 3, 4, that's our second group. And 1, 2, 3, 4, that's our last group. So that's how easy it is to create a quantile classification. Now the last type of classification is called natural breaks, and again we need to first sort the data, so let's go ahead and do that. Now for this one we need to figure out the biggest jumps in data of consecutive data points. So the best way to do this is to create a difference for every single pair of values. So first we'll do 103 minus 102, and then we can do 121 minus 103, and we could continue to do this formula for each of these values, but a much easier way is to take this square at the bottom right of the cell and click it and drag it down. What this does is it takes the formula in here and it just drags it down to each cell. So if you look in this cell, it's B5 minus B4. This cell is B6 minus B5, and so on. So it just iterates through the cells, changing the formula to match the previous one. So now we can see where the biggest jumps in the data are. So the first major difference is this 49. So between these two cells, there's a significant jump, which means that this is our first grouping. So let's go ahead and color these blue. The next biggest jump is 18. So between these two is the second biggest jump. So that means this will be our second grouping, and this will be our first grouping. So although it's slightly less intuitive, it is just as easy to create these groupings. Now if we look at the differences between equal interval, quantile, and natural breaks, we can see there is a significant difference in the way the data will be represented. In equal interval, our first grouping is pretty big, and the other two groups don't really have that many values in them. You can see quantile is equal throughout, and natural breaks only has a couple data values in the first group, and most of the data values are in this middle group. So you can imagine if you're representing this data in a map, for instance, the three different classification methods would show very different things. So you have to be careful when you're reading maps that you understand the classification method, and you also have to be mindful about picking a classification method while you're creating data representations.